Okay. Good morning to all. Now we are starting our thermochemical conversion technologies. We already started this class, previous class itself. Previous class we completed briquetting. It also comes under thermochemical conversion. You know that thermochemical conversion is divided into three categories. One is combustion, pyrolysis, and gasification. Today we are going to see combustion. Combustion is very important one. In all other, even biochemical and chemical and thermochemical, combustion process is the first conversion technology human followed. That is by firing. It's already incineration, just firing. The firing is itself burning. Burning itself is called combustion. So first, the process, conversion process, energy conversion is combustion. That's why it is very important. All our stoves, ordinary wood stove to our very big furnaces, even thermal station, power station furnaces are combustion process. So combustion is very important. We are going to see combustion today. So the combustion is a rapid oxidation of fuel producing heat. So we are producing heat through combustion. It's an oxidation. As you know, all the fuels contains hydrogen, carbon, and some amount of sulfur. So the oxygen combines with the carbon and hydrogen, and oxidation takes place and it produces heat. That is, combustion is a rapid oxidation of fuel producing heat. Fuel is burnt in excess air in a controlled condition to produce heat. We are not controlling air supply, but the environment is controlled, and we are providing excess air in addition to what it is required. As you see in this three-stone stove or in other combustion furnaces, we are providing air, 100% air. That is, we are providing entire oxygen to burn entire fuel. Flue gases from the efficient combustions are carbon dioxide, water vapor, with the fractions of other elements. What is the exhaust gas? After burning, the flue gas is carbon dioxide, water vapor, and elements. Combustion heat is used to raise steam in a boiler that is used to produce electricity. So through combustion, we are producing heat. That heat is used to produce steam. So all steam boilers, all industries which are dependent on steam is by combustion. Even thermal power stations, it's steam. Steam is producing power. So, and another is cogeneration. You know, in our sugar factory, we are producing heat and power, both heat and power. That is cogeneration. We are generating heat and also power. And also that biomass can be combusted with fossil fuels. So in addition to our biomass, we can add some fuel like coal or diesel. So combination of both. So that is called co-combustion. So these are all the combustion. The important of the principles of combustion is complete combustion of a fuel is possible only with adequate supply of oxygen. You know, the 20.9% of oxygen in volume is in the air. So we can provide air. That way we are providing oxygen or oxidation. Combustion take place. So complete combustion, we have to provide 100% air. So 100% oxygen. And the first process starts solid and liquid fuels changed into gas and burnt. So when we burning it, first gas comes out and the gas becomes taking secondary air and it burns. Out of 100%, 79% is nitrogen. So due to nitrogen presence, it reduces the efficiency because it dilutes it is not a combustible gas. That's why it's a dilute the efficiency and increase the flue gas. That exhaust gas will be increased. And also it is toxic. It produces nitrous oxide like that. So it is inefficiency is due to the nitrogen. And the carbon dioxide, water vapor, and sulfur we are producing. It releases heat. It contains heat of 8,084 kilocalories from carbon dioxide. The water vapor 28,922 kilocalories, and sulfur dioxide releases 2,224 kilocalories of heat. If 1 kg of carbon monoxide forms, if carbon monoxide, it is an incomplete combustion. When the combustion is complete, it produces carbon dioxide only. When it is an incomplete, there is a carbon monoxide, CO. Carbon monoxide, because there is not enough oxygen to burn entire carbon. That is, it releases as a carbon dioxide, carbon monoxide. It comes with the flue gas. So the loss occurs due to incomplete combustion. The loss occurs. So with the loss of heat is 5,654 kilocalories of heat. So it's a direct combustion system. We are supplying fuel and excess air. There is combustion take place in the furnace or stove. It produces hot gas. That hot gas heat the boiler. The boiler produces steam. The steam is used to run engine or turbine. From the engine or turbine, we are getting power or heat. And the exhaust gas goes, we are cleaning it, and cleaned flue gas is let into the atmosphere. This is a direct combustion system. There are 3 T's in combustion, very important categories, important characteristics of this combustion process. That is temperature, turbulence, time. Yes, already we had seen that a temperature is very important. So temperature high enough to ignite and maintain ignition of fuels. So to ignite it, to start to ignite, we need a high temperatures. And next, the turbulence, mixing fuel and oxygen. So oxygen to mix with the fuel, then only it burn completely. So the turbulence is very important, and time sufficient to complete combustion. To take combustion to take place, we need so it's the 3 T's. There are 3 types of combustions. One is perfect combustion, or correct air and or excess air. We provide excess air, that it is a perfect combustion. Good combustion also occurs when we are providing correct air and fuel, correct amount of fuel. Whatever fuel you are supplying, the required air is we are supplying. Incomplete combustion, unburned carbon. We are not supplying enough air, so the carbon is unburned and it produces carbon monoxide. So efficient combustion, these are all the conditions. Higher than psychometric amount of air must be supplied for complete combustion. We can see how we are calculating the stoichiometric amount of air. Then the fuel and oxygen in the air must be in free and intimate contact, that is turbulence, mixing. Then third, the volatile combustion products must be intimately mixed with the secondary air. So when the volatiles burns, first it comes out as a gas and it burns. It is a flaming, we can call it as a flaming. And another is carbon, it is glowing, just like it. The volatile combustion products leaving the fuel bed must not be allowed to cool below the ignition point until the reactions are completed. So in and around that stove, we should not allow to cool it. When it is cool, the efficiency becomes less. And the volume of furnace is enough to accommodate the expansions. That is, that should be designed that the provision for expansion of the gas during the process of combustion at high temperature is made. So we have to provide enough space for the furnaces. That you can see types of combustion. First, it is a perfect combustion. We are supplying excess air, whereas in good combustion, we are supplying correct air. Incomplete combustion, we are not supplying correct air, enough air. This 3 process, you can see in your book also this drawing. So another the stoichiometric, we say how much air is required. So how much carbon, how much hydrogen and sulfur is available in the biomass. Based on that, we are supplying the kg of the percentage of air based on the fuel. So we get a formula. If we need a perfect combustion, how much of air is required, psychometric air is required. For that, there is a formula. If we can find out the carbon, hydrogen, oxygen, and sulfur in the fuel and substitute in the formula, we will get the psychometric air requirement. And the excess air required for gaseous fuel is typically above 50%. We already told that this combustion needs excess air. How to calculate the excess air? So 20.9% of air is oxygen. That is a percentage of oxygen is measured, and the percentage is calculated with respect to the excess air requirement. Further, this is a formula that is excess air percentage is equal to percentage oxygen percentage measured divided by 20.9 minus percentage of oxygen measured into the 100. From this we can calculate excess air. It is around 15%. So combustion efficiency, how we are calculating the combustion efficiency? Combustion efficiency is determined by subtracting the heat content of the exhaust gases expressed as a percentage of fuel's heating volume from the total fuel heat potential or 100%. Thus the combustion air percentage is equal to 100 minus how much stacked air, how much heat is goes with the flue gas or goes with the exhaust. That we reduce from the 100, we will get the percentage of how much percentage of the efficiency is there. So based on the combustion, there are four designs of chulas. Chula means in Hindi it's stove. Improved chulas means improved stoves or improved furnaces. In TNAU we developed four units, and we are going to study the 4 units. There is a single pot chula, double pot improved chula, TNAU noon meal improved chula, biomass gas stoves. There are 4 types of chulas, stoves developed by DNAU. That the characteristics and advantage and disadvantage and efficiency we are going to see in the class. Single pot chula, you might have seen in the practical class. It's a okay. There is a problem. Some of them are not able to join. They had informed me through message. Don't worry. Next time we can find out the fault where we are lacking. That can be fulfilled. But the recorded one, we are recording it. The recorded with the presentation we will post in the classroom, Google Classroom. They can see from that, and you can advise your friends to see the recorded one and from the Google class. Next time you will see what is the problem in it, and also they ask them to attend the quiz. Finally we ask them questions in the classroom. You can answer the classrooms. That will be enough for the attendance. Okay, let us go for the class. Single pot chula. It's a towel wall cap. It is a concentric towel wall. In the inner there is a cap, the air cap. The air will be the inner and it will be supplied. I am going to show you the single pot chula next slide. Now you can see that the grate at the bottom where the combustion chamber is provided. Small 5 legs, 5 centimeter. It is to stand. 2 rectangular air openings in both sides. Lower portion of the outer wall of air. It is for entry of air. Inner wall, 1 centimeter diameter holes are inside the wall. There is 1 centimeter diameter holes. From that holes, we are supplying air to the fuel. The secondary air enters through the rectangular openings and heated in the concentric base. And then again, it was supplied to the, just like our blowing, Udu Kulal blower, we are blowing inside naturally. That's a preheated air helps in proper burning of the same. The efficiency of the single pot chula is 24%. See, this is a combustion chamber. The one is our line diagram, and another is we are burning it. And both sides we are providing. The central side we are providing we are supplying the fuel. In it, there are 2 concentric cylinders. Inside there is a stove. Inside there is a holes. From the holes we are supplying it. When the hot air goes up, the inside air goes to and burns it. So it supplies oxygen and it is a complete combustion taking place. due to compression produces heat. That is what happening. You can see the flame and also the bottom the ignited char. In the same way, the towel wall also, we are extending the chamber. From that, we are outer wall extended to our second part annual chamber with a 3.5 centimeter. Two secondary air inlets are rectangular, the same size, bottom of the first chamber and bottom of the second part is provided. The same holes are provided in the inside wall of the air, just like our single part. The efficiency of towel part improved Chola is 26%. You can see the towel walled combustion chamber. So there is a two part. We can use one part and the waste heat also utilized here. So from that we can simultaneously cooking and making another side dishes also. That's why we call double pot. So it is bigger than that towel pot, and we are providing chimney. It's a noon mill scale. At the time, there is a need for a combustion chamber, that is a stove, wood stove for the entire noon mill scale. So TNAU developed this one. Here we are providing bigger air inlets, and the first hole is 40 centimeter and second part hole is 48 centimeter with the chimney. This is a noon mill scheme. It is also the efficiency is around 26%. And another is a biomass gas stove. The biomass gas stove is a natural damped gasifier. We are using the potter's wheel, making a cylinder-like material. That cylinder, we are providing all necessary inlet and outlet for the cylinder. That is called biomass gas stove. Why this comes under stove? It is a gasification unit. We start in combustion mode, then it automatically changes into gasification mode, combustion mode, then gasification mode. This is a cylinder-like material, natural convection type, updraft gasifier, cylindrical body made of clay, sand, and paddy husk. We are mixing clay, sand, and paddy husk, and from the mixed clay, we are making the cylinder using the potter's wheel. Potter's wheels means satti pana seyyakuriya wheel. From that, we are making the cylinder, and the top of the cylinder is closed, and we are giving air holes for secondary air. In the bottom also, we are providing air holes below the crate, and the air hole is used as providing primary air, and we remove the air. That is the diameter of this biomass gas stove is 290 mm, and the height is 630 mm. Iron crate for biomass, holding the biomass, we are providing from the above the base, that is 50 mm above the base, the bottom. The holes are provided in the top for secondary air circulation. There are 3 holes provided in the top. Feedstocks, what are all the feedstocks we are using? What are the fuels that is appropriate for biomass gas stoves? Wood chips, all agricultural residues, such as coconut shell, groundnut shell, arecanut husk, etc., all in the form of small chips. We have to make it as splinters or small chips, cut it into a small silver and used as a raw material, that is a gas feedstock for the biomass gas stove. So this mounted biomass, inside there is a cylinder, and it's the airlet is provided, air inlet is in the top, it's a secondary air inlet. Gas removal as well, primary air inside is the gas removal system is provided, and the cooking vessel is placed in the top. This is mounted in brick masonry. The cylindrical part, that is cylindrical biomass gas stove, is mounted inside the masonry of brick masonry, inside the brick masonry. To give a strength to the stove, we are using the brick masonry for the stove. So how it works? It can be ignited in 2 methods. One ignited in the bottom, and the other method is ignited in the top. So we can inverted gasifier or directly the gasifier. We can put all the first started in combustion mode and change it into gasification mode. First we put all the materials, what are all the materials, and ignite in the top. Or already we want to ignite from the bottom, first we can put charcoal, ignited charcoal inside, and we can fill with our whatever feedstock. Then automatically the gas production starts burns. First, there's a combustion mode, and automatically it become a gasification mode. It burns just like our burners, gas burners. The gas stove burns. We can application is a small agriculture and allied industries. All agriculture related, even for cooking paddy cooking in the rice mills, small scale rice mills. In arikanut form, we can cook arikanut, boiling arikanut, boiling turmeric, and all other industries, wherever it is required, instead of furnace, we can go for biomass gas stove. So this is our combustion. There are five different types of materials we are using combustion process. So combustion is a open burning. Otherwise, we call it as incineration. And all our stoves, from wood stove to furnaces, bigger furnaces used in the thermal plants, are based on the principles of combustion. Combustion, it takes oxygen and produces heat. Combustion, we are producing heat, and it produces carbon dioxide, water vapor, and small amount of other traces of other gases as a flue gas. So combustion is the mostly using heat producing thermochemical conversion process. So this is our combustion process. Already we had seen the briquetting, and the briquettes can be used as a raw material for the all stoves and furnaces. Next, we are going to see pyrolysis and gasification. But this class, we are only seeing combustion. So you again see the supply of air is very important, and the design of stoves, how you are supplying the air, primary and secondary air. These are all the very important points. And what are all the feedstocks used in combustion process? The combustion, based on combustion, single part, double part, Nunes mills, and biomass gas stove. These are the four gadgets developed in TNAU. So this is our class. You can go through our presentation again. The presentation will be posted in the placed in the uploaded in the classroom, Google Classroom. You can again and again go through the materials and the presentation, and you can vulgarize in combustion process. Thank you. So one more. There is a quiz. Assignment will be sent to you Google Classroom. Kindly attend the quiz and get the attendance. So for those who are even not attended, they can attend the quiz. So the attending quiz will give you a mark and as well as your attendance. So to get an attendance, you have to attend the quiz in the Google Classrooms. So only attending Google Classroom and fulfilling the quiz answers, giving the quiz answer only, you will get the attendance. So automatically the Google Classroom put your attendance, and marks also it will communicate to you. So this integrated part, so you can compulsory follow the process, and ask your friends, those who are not able to attend also, to attend the quiz and